Hi, my name is Navid Ishrak. I am a second year PhD student at Peace Lab. Currently, the project I am working on is an AC to DC power factor correction converter for EV onboard charging applications. So as you can see, this is my hardware prototype. So the topology for this we have used is a flying capacitor multi-level topology. As you can see here, I will discuss the control and operation of flying capacitor multi-level totem pole PFC converter in more detail. The four-level FCML PFC topology is illustrated here. The switches Q1B, 2B, 3B and Q1A, 2A, 3A. These are the high frequency switches operating at 100 kHz, and this forms the flying capacitor multi-level leg. The switches S1 and S2 operate at line frequency 60 Hz, and this forms the line frequency leg. The flying capacitors are the C1 and C2, and the output DC link capacitance is C out. During the positive half cycle, the S2 will always conduct, and Q1B, Q2B and Q3B will be acting as the active switches. During the negative half cycle, S1 will always conduct, and Q1A, 2A and Q3A will be the active switches. The main advantage of the flying capacitor multi-level totem pole PFC converter are that it enables a fraction of the output voltage across the switches. So for a 4-level totem pole PFC converter, the voltage across the each switches will be 1/3 of the output voltage, so which enables us to use devices with a lower voltage rating. There is an increased equivalent ripple frequency of the inductor current, which can reduce the inductor size by 1/3 for a 4-level totem pole PFC converter. The switches operated at 1/3 the frequency of the inductor current, resulting in a lower switching loss. Thus, if our inductor current ripple frequency is 300 kHz, our switches will operate at only 100 kHz. Moreover, the switches with smaller RDS on are also utilized to minimize the conduction loss. The operating principle of the FCML PFC is discussed here. The switching states of the FCML PFC is shown in the following table for all possible cases. The flying capacitor C1 and C2 charging or discharging or no charging conditions are also shown here. VSW is the switching FCML leg switching node voltage with respect to the ground. This following waveform is for the condition when duty cycle is between 2/3 and 1. That means the input voltage is operating between 0 to V out by 3. These are the carrier waves for the switches Q1B, Q2B and Q3B, which are 120-degree phase shift apart. Due to this phase shift PWM, the effective inductor current frequency is thrice the switching frequency. In one switching cycle of a FCML PFC converter, there are 6 switching states. See here at the first stage, the Q1B, Q2B and Q3B all are on, and no current flows through the capacitor, flying capacitor C1 and C2, and the inductor voltage is VAC. In the second switching state, which is 101, the current flows through Q3B, discharges the flying capacitor C1 and charges the capacitor C2 and completes the path. Here the inductor voltage is VAC minus V out by 3, which is negative, so the inductor current will be having a negative slope. The third switching state is again 111. That means the voltage across the inductor is VAC, so the inductor will be charging at a positive slope. The fourth switching state is 110. That means the current will flow through Q3A, charge the capacitor C1 and complete the path. No current will flow through the capacitor C2, and the voltage across the inductor is again VAC minus V out by 3, so it will have a negative slope. The fifth switching state is again 1 1 1, and the last switching state, which is 0 1 1, here Q3B and Q2B will be conducting. The capacitor flying capacitor C2 will discharge and complete the path. There will be no current flowing to the flying capacitor C1, and the voltage across the inductor is VAC minus Vout by 3, which will again have a negative slope. The previous slides discussed the switching state when the duty cycle was between 2/3 and 1, and the input voltage was between 0 to 1 Vout by 3. These two cases are when the duty cycle is between 1/3 to 2/3 and 0 to 1 by 3. So for the other parts of the line cycle, these two conditions will be applicable. Similar again, in these cases, the inductor current frequency is 3 times the switching frequency, and again the Q1B, Q2B, Q3B all are 120 degree phase shift apart. The inductor voltage behavior across half the line cycle is shown here. As you can see, there are 3 different segments which have been divided into 0 to Vout by 3, Vout by 3 to 2 Vout by 3, and VAC greater than Vout by 3. In all of these 3 different segments, we can see the maximum voltage across the inductor is Vout by 3. The control block diagram of the flying capacitor totem pole PFC is shown here. Here there are 2 different loops, inner current control loop and outer voltage loop. At first, the output voltage is compared with the desired reference and go through a PI control compensator. So PI compensator has been realized using the bilinear transformation. The PI compensator output is multiplied with the input voltage to get the sign reference, and this output is the current reference, which is again compared with the inductor current. After that, this goes to the current loop compensator, which is added with the feed forward term and goes to the phase shift PWM control logic. The duty cycle over the complete line cycle is shown here. So this is the FCML PFC hardware prototype that we have designed in our lab. So this is a modular architecture where we have used daughter cards. This is the FCML daughter card, which has 6 200 volt EPC GaN switches with bootstrap circuitry with only one single power supply. On the bottom side of the PCB, we have used the flying capacitor 1 and flying capacitor 2. Next, here this is the line frequency leg daughter card. We have used 650 volt GaN system switches, and for the control part we have used a DSP. From the main board, the input voltage AC voltage comes here, goes to the EMI filter, and then goes to the line inductor. So as you can see, the line inductor is very small because of the effective frequency to be thrice in this topology, 4-level FCML topology, which then goes to the switching node of the FCML leg. On the other side, here is the DC link cap, 660 microfarad, and this is the output voltage. Now to demonstrate the operation of the FCML PFC converter, we are going to run our hardware. As you can see, the current is already settled now. can see, this is the experimental results for the FCML PFC for an output power of 1 kilowatt. This is the DC link voltage, which has 400 volt and with the 120 Hz ripple, but very negligible. Here is the input voltage, is the 120 volt AC RMS. Next, the red one is the inductor current having 8.8 ampere RMS, that means like 1 kilowatt. This green waveform is the switching node voltage between the FCML leg switching node and the line frequency leg switching node. As you can see, there are 3 different levels: 0, VC1 and VC2. So the level difference, the voltage difference in each level is V out by 3. So in this first level, it is like it deviates from VC1 to 0, and the second level it deviates from VC2 to VC1. Now we are going to take the load transient results from 1 kilowatt to 500 watt and then again to 1 kilowatt. These are the load transient results from 1 kilowatt to 500 watt and again to 1 kilowatt. So at 1 kilowatt the current RMS is 8.8 ampere RMS, at 500 watt it is 4.2 ampere RMS. So from the output DC link voltage, when it was initially 400 volts, then it shifted from 1 kilowatt to 500 watts. So there was an overshoot of 12% and it again settles down to a 400 volt in 0.2 seconds. Similarly, when the power level is from 500 watt to 1 kilowatt, there is an undershoot that is about 10% and again settles down at 0.25 seconds. This is the flying capacitor 2 voltage and the flying capacitor 1 voltage, which has also satisfactory overshoot and settling time, so which demonstrates that the outer voltage control loop and the inner current control loop are working properly.